Okay. So till now in this particular topic, we have discussed what is process, what are the data structures required to manage that process, and what are the different states of the process, okay, which characterize the behavior of that process. So that is what we have already discussed. Now further, today we'll be discussing the process control itself. Okay, we'll be discussing process control, and then after we'll be discussing process management in Unix System 5 Release 4 as a case study. Okay, so you must be knowing this, that there are two modes of execution for any process. Normally, in most of the operating systems, in general, there are two modes of execution for a process. One is a privilege mode, another is a user mode. So user mode is less privilege mode, and user programs typically execute in this mode, whereas system mode is more privileged and kernel of the operating system executes in that. Now, till now, you must be aware that within operating system, there are mainly two levels of programs. Those applications that we run as user, they are called user programs. But our application may be also using some of the code from the kernel itself, the operating system support. Like simple example, if you want to read a file in your program, if you want to read a file, whenever you use any library from your programming language, internally that library is using kernel code so that it can open that file and give it to you. So that kind of kernel code, which is more privileged, right, which is which needs to be secured from the user intervention, so that kind of code gets executed in system mode or kernel mode. Otherwise, the application that we run, they are executed in user mode. So there are basically two modes of execution for any process. The functions of OS kernel. Now, what kind of functionalities are provided by OS kernel? Okay, let me ask those students, the new students, are you aware of the concept called kernel? Please interact so that I can get an idea at which stage you people are. Are you there, new students? See, if you do not interact, this will become a boring lecture from one side only. It would be like I am coming here, just speaking something and going back. This is not going to be useful for neither side, not for you nor for me. So please be interactive and let me know at which stage you people are. Do you know what is kernel? Okay. Priyesh bhai, are you there?
Yes, sir.
So what's the case? I mean, why they are not interacting? I mean, how would I go further? Otherwise, if I don't know at which stage they are, how would I go further? I mean, it won't be possible for me to club these two different students. I mean, please ask them to talk to me or at least give some feedback.
Students from second section, please interact with us, sir. At least let him know what is going in our last lecture. Actually, only there it will be possible for him to go further.
Yeah, someone has
So
messaged me that they did kernel part. Okay, fine. Now it is completely up to you people. If you are interested, please interact when I ask. Otherwise, it will be only one way. I'll just come, speak, and go. Okay. Fine. So when we talks about functions of OS kernel, one of the main function is process management. And what are the part of this process management? What functions are there inside this process management? What activities it provides? Process creation and termination, process scheduling and dispatching, process switching, process synchronization and support for inter-process communication, management of process control blocks. In fact, to do all these things, it needs to manage process control block. So that is one of the important functionality. Another important functionality, memory management, allocation of address space to processes. It has to provide some space to those processes. It needs to manage swapping of these processes from main memory to secondary, secondary to main whenever required. Page and segment management. Nowadays, the hardwares which are there, modern day hardwares, they provide paging and segmentations within for the memory management. So that has to be managed by this memory management function of the kernel. Then it has to perform IO management by managing the buffer spaces. It has to allocate IO channels and devices to processes. So those devices, IO devices, that they need to be allocated and managed, okay, by this OS kernel. And some other support functions like interrupt handling, accounting, monitoring. These are the some support functions which are provided by OS kernel. So now, as we are talking about process control right now, let us discuss process creation. Okay. So once the OS decides to create a new process, what it does, what OS does when new process has to be created. First of all, it assigns a unique process identifier, process ID, then allocates space for the process. After assigning ID, now it has to allocate some space in the memory so that required stuff can be put inside the main memory. So allocate space for the process, initializes process control block, the most important part of any process, PCB, that gets initialized, sets up appropriate linkages. Now linkages means this PCB contains so many information regarding that process, where the program data is, where the where the program code is, what are the shared memories, what are the file tables. So all those linkages has to be set. So set up appropriate linkages, creates or expand other data structures if required some other, if it requires some other data structure like file tables, and so it will create those data structures and assign to that. So these are some broad steps, I can say very overview I'm giving you, that what kind of steps are performed by OS when it creates a process. Now the concept comes that say switching processes. Now first of all, we need to understand what is process switching. Okay, so whatever discussion we are doing, we have assumed that we are doing it for the single processor. So this OS discussion that we are doing, it is by the perspective of single processor. Now, when you have a single processor, still you get a feel that there are multiple programs which are running in your system. Okay. So how you get that feel? If it is a single processor and still you are running multiple applications, so how you get that feel that your applications are running in parallel, though you have a single processor? Because if you have a single processor, at a time only one process can run. So would anyone like to answer this? Okay, fine. So the idea is, for small amount of time, one process is executing on the processor, and after that immediately some other process runs, and this amount of time that is given to each process to run one by one, that amount is so small that as a normal user, end user, we can't identify that okay, currently which process is running. And the final effect that you get is that all processes are running. That is the final effect. As a user, we get that same effect. Now when, let's say you have assigned, I mean OS has assigned X amount of time for every process to run. Okay, so currently process A is running. After X amount of time, now process B or some other process will run. That OS will decide which process will run, right? Now, to execute now other process, whatever is executing right now, it has to be saved, and some new process will run on the processor. So when one process goes out and another process runs in the processor, that is called process switching. That is called process switching. Your processor is switching the processes. Okay, so there are several design issues which are raised regarding process switching. Now, to perform process switching, OS needs to take care of certain questions, like what events trigger a process switch. When that happens, when process switch happens, I have given you a simple example. When the allocated time, if it is over, there will be some interrupt generated, and while handling that interrupt, OS will come to know that, okay, that this process time is over and I need to assign another process to the processor. That is one possible reason. Then we must distinguish between mode switching and process switching. Now, we just discussed in the starting of this lecture what is mode switching. Process can run in user mode or kernel mode. So more privileged mode is kernel mode. Now, sometimes when you are running your program, as I just discussed before also, you need to open a file. But file opening library that you have, internally it executes some kernel code. And that kernel code will be executed in system mode or kernel mode. So there is now change in the mode, the switching in the mode from user mode to kernel mode while handling certain code. Okay, so that is mode switching from user mode to kernel mode, but process is still same. That is your program which is running C program, let's say, and it is asking for the file. It is opening a file. So while opening the file, mode switch will happen from user mode to kernel mode, because now you want to execute some privileged code. So that is mode switching. And process switching is different. The whole process itself gets switched. It goes out and new process will be executed. So you need to understand the difference between mode switching and process switching. What must the OS do to the various data structures under its control to achieve a process switch? Okay, so there are various data structures that process handles to control that. So that we will see. So these are the certain questions that need to be answered while handling process switching. First is when to switch process, right? Which events or what events trigger a process switch? So again, a process switch may occur anytime that the OS has gained control from the currently running process. Okay. And possible events giving OS control are, what are the possible events when process switch happens? When there is an interrupt. Interrupt is one mechanism which is external to the execution of the current process. Now, there are few reasons because of which there can be an interrupt. And whenever there is interrupt, OS will identify that and accordingly it will switch the process. Then there is another kind of mechanism called trap mechanism. Interrupt is something which is external to the execution of current process. When your process, let's say your process is running, okay, and some other process before your process, it was waiting, it was blocked on some event. Now that event has occurred and that interrupt is delivered to the processor. So processor needs, I mean, OS needs to identify that interrupt. So that interrupt basically it is coming from outside environment. It is not within the process. But while your process is running, and let's say you are trying to access some memory, okay, and that memory area is not available. So that is called trap. So that is associated with the execution of the current instruction. So that is another mechanism. Okay. And third is supervisor call. The same example. Let's say your program is trying to open a file. In your program, you are using a library, but that library internally it is executing kernel code. Okay. So because of that also sometimes what happens, let's say you want to have some file, kernel code will be executed to open that, but kernel has identified that that IO device on which that file is, it is busy and it will take some time. So what is the possibility that your process who has to wait for that file, it will be sent into the block state, and as it is sent into the block state, new process need to dispatch to the processor to execute. So these are some mechanism, or these are some reasons why process gets switched. Either some interrupt is there from outside, either there is some trap within your process, or there is some supervisor call because of which your process can be blocked and other process may be executed. So these are some mechanism because of which a process can switch. So does this make sense? Yes, guys, does this make sense?
Yes, sir.
Yeah, okay. So that is one point that we handle. Another is distinguishing between mode switch and, okay, these are the examples of different types of interrupt. So what can be the interrupt which is external to the running process? Clock interrupt can be there, like time is over. Your process time which is given to you, it is over. So there is a clock interrupt. And because of that, process need to switch and another process will come. Another is IO interrupt, just discussed that some event on which previous process was waiting, that event has happened and it will be and that will be delivered, that interrupt will be delivered to the OS and OS will handle it. So while handling that interrupt, it is possible that process may be switched. Trap, like memory fault, you are trying to access a memory from your process which is not allowable, which is not allowed, or which is not there. Invalid operation, maybe you are trying to do some divide by zero kind of operation. Okay, some trap, some kind of error situation, that is called trap. And then I just discussed system or supervisor call. We discussed that file opening example. Now, what is mode switching? Though we have already discussed different modes, let us discuss a little bit more about mode switching. So when a running process changes its mode from one to other, there are mainly two modes, user mode and kernel mode. So one mode to other mode, then it is called mode switching. While switching the mode, processor state information of PCB. Now, what is PCB? If you remember PCB, it contains three categories of information. One is process identification information, second is processor state information, and third is process control information. So second is processor state information, which mainly contains different types of registers. So when switching between mode happens, while switching the mode, only processor state information of PCB is saved. Okay. When you go from user mode to kernel mode, and that information will be restored back when you come back from kernel mode to user mode. So if we talk about PCB, as I just discussed that, there are three categories of information that we maintain in PCB: processor identification related information, processor state information, and process control information. When mode switch happens, only processor state information needs to be saved and restored. But when process switch happen, more information need to be saved and restored. So process switch is heavy than the mode switch. Are you getting this? So process switch takes more time, while mode switch requires less time because it needs to save less information. So this is one example of mode switch. I have taken this figure from tutorial point. This is user mode, this is kernel mode. Let's say your process is getting executed. Now you want to call some system call. Let's say you are trying to read a file or you are trying to write to the file. So you are using library, but that library is actually required some system call. Okay. So this is one kind of trap. Mode switch happens. Okay. And mode bit equal to 0. Now you set mode bit equal to 0. It means you miss OS will do that. It means that now process will be executing in kernel mode and that system call will be executed, and then after it will return back to user mode. So mode bit will be again reset to 1. So this is how mode switch happens. But when this switch happens from user to kernel and kernel to user, some information, mainly processor state information, needs to be saved. Okay, and that same information will be restored back when you come from kernel to user mode. So what are the steps involved in a process switch? Now we are discussing process switch. Mode switch is done. Now we are discussing process switch, steps involved in process switch. So save context of processor, including program counter and other register. First of all, the processor state information, the registers information, they are saved. Okay. Update the process control block of the process that is currently in the running state. So PCB needs to be updated of the process which is currently in the running state and going out. Move process control block to appropriate queue. Now your process which is currently executing and going out, so PCB of that process has to move to another queue, maybe ready queue or block queue or ready suspend, depending on the situation. Now select another process for execution. So basically these three steps, they are related to the currently executing process and which is going out now. For that, these are the steps related to that. Then OS needs to select some other process for execution, that is called scheduling. Update the process control block of the process selected. Now the PCB of the newly coming process will be updated. Then whatever memory management data structures are related to that new process, new means the process which is coming to execute, that process data structures will be updated and restore context of that selected process. Now whatever was the context, like processor information, processor state information, that means all register information and other things, they will be restored. If that process was before there, I mean it was there before and it was stopped because of some reason and it is coming again to execute, so state or the context of that process will be restored. If it is a new process, new information will be updated, I mean new information will be loaded. So basically restore the context of the select. So this are the 7 steps which are involved in process switch. And when we talk about mode switch, only this thing is required. Save context of processor, including program counter and other registers. And when you move back from kernel mode to user mode, this will be restored. So basically there are only 2 steps in mode switching. But when it comes to process switch, multiple steps. There are a number of things that you need to do, OS needs to do. And that is why process switch is heavier than the mode switch. Are you getting this? Are you getting the difference between mode switch and process switch and when which is required? Yes. Okay. Please ask question if you have any at, in the middle of the lecture also. Now, is OS a process? A big question. What is OS? We have seen that OS is nothing but a software. It is a code, it's a program which is there in between our application programs and the hardware. It is there in between our applications that we run and the hardware. So OS is one interface. But is it itself a process? I mean, when we say OS code gets executed, it is executing something, driver is executing or something like that. So is it itself a process? Because normally when you run anything, that is called a process. When you want to run any program, first it will convert into the process and then it gets executed. So this is a big question. Okay. Is OS a process? So now it depends on the design. It depends on the design. So if the OS is just a collection of programs and if it is executed by the processor, just like any other program, is the OS a process? If so, how is it controlled? Because if anything is a process, it has to be controlled by OS. If OS is a process, can OS control itself? Okay. And yes, if it is controlled, then who or what controls it? So these are some questions which are related to this idea that whether process OS itself is a process or not. So again, it depends on the design actually. These are the three different designs that I have presented here from the book, which is given in the book. But nowadays, very different designs are available, and there can be mix and match also. Okay. So one simple design which was followed in some older operating systems, that is this design, where this kernel itself is a separate thing. It is not a process anymore. It is itself a different thing. Okay. It is not considered as a process. This idea of process was not applicable to this kernel programs or OS programs. It was not applicable, though it has its own memory structure, data structures, and everything. It has its own stack. It was executing, it was executing, but not part of any process. It was separately executing, but it was not considered as a process. Though it was executing, it was not considered as a process because it was completely a different entity, a separate entity. So that was the design which was followed in the older designs, older operating system designs. Another design, you can see that this process P1, it itself has some OS functions which are executed. So simple example that I would give here, the same example, let's say your process is running, your program is running, and it has to open a file. So that file opening, system call will be executed in the kernel mode. So what happens, your process will not be switched. It will execute that kernel mode, that functional file opening code, kernel code will be executed within the context of the same process P1. Okay. So kernel code is also executing in the same process, but it is executing in a different mode, kernel mode. So this is another design where most of the OS function, I am telling you most of the, not all, most of the OS functions or OS code, it will execute within the context of the process itself, and remaining some part of the OS like process switching function, it may be executed similar to this idea that it is executing separately. It is executing separately. Okay. And the third design where most of the operating system code itself is one process. Here, this OS functions, they are not different process. That is part of some user process. Here, that OS functions, they are separate processes itself, and they are executing as a different separate process. So this is another design. Are you getting the difference between these three designs? This is more, like microkernel kind of design. This third one is more like microkernel design, where most of the modules, operating system modules, they execute as one process, and that is a special process. Okay, here OS functions or OS code that gets executed within the context of the process, right? So first is non-process kernel. This design, kernel runs outside the context of any running process, and it has its own memory and stack. The concept of process is considered to apply only to user programs. Operating system code is executed as a separate entity that operates in a privilege mode. This is separate entity that is operating in privilege mode. Then second style, execution within user process. So if you remember PCB and then process image, this is process image. But if you compare this process image with our previous diagram, one extra thing is added, that is kernel stack, because now kernel functions are also executing within the same process, and within kernel again it has few procedures that need to be called from one to other, and because of that it requires some kernel. So kernel stack is also there. Kernel stack is also there. So this process image that we discussed previously, in that one extra thing is added, that is kernel stack, and this shared address space, mainly this is OS code. So operating system software within context of a user process. Operating system code gets executed within the user space. No need for process switch to run OS routine. Okay. You need not to switch process if you want to execute OS routine, except few examples, except few cases. And the third one is process-based OS. Implement the OS as a collection of system process. See, implement the OS as a collection of system processes. Encourages a clear design. Definitely, it's a clean design, because different OS functionality, it is a separate process, and it is useful in a multi-processor system. Definitely, it is useful in multi-processor system, because one OS function can be executed in one system, another can be executed in another processor. So definitely this helps, because when you have multi-processor environment, and if you have different things executing as different processes, they can be executed in parallel. They can be executed in parallel. So that is the idea. This is more like microkernel architecture. So I hope that idea is clear. What is process creation, then what is process switch, what is mode switch, how OS process itself gets executed. I mean, what are the designs? Should I consider that you are getting that? Do you have any question, or you are just listening? Because this is not going anywhere. If you are just listening and you are okay with that, and you don't understand, or you are not asking any question, you are not getting any benefit out of this 1.5 hour that you are attending this lecture. And I don't want to make it that way. I assume, I mean, I understand that, of course, this is a very theoretical subject, and this is like, something out of blue, because you cannot even see that. Like programs, normally when you run programs, you can see what is happening. Here you can't see that. It is pure theory, design theory. So I understand that it is difficult to digest and difficult to visualize, but still, if you put some efforts, definitely it will help. Definitely it will help. So be interactive, ask your question, ask your doubts. Next is one case study that we are going to discuss very briefly. Of course, we are not going to, because this is the whole subject itself. UNIX OS design, it is itself a whole subject, and more than one subject, in fact, if you want to really learn the design of this UNIX operating system. Okay, but very briefly we are going to discuss this, and whatever we have discussed till now in this chapter, we are trying to relate that idea in this case study. Okay, so let us discuss this UNIX SVR4. SVR4 stands for System 5. V is actually Roman 5. System 5 Release 4. So UNIX SVR4 uses the model, that is B model we have just seen. OS functions get executed within the context of user process. This is the design of UNIX SVR4, where most of the OS executes in the user. Most of the OS, not everything. There are few things, there are few code of the OS or the kernel which does not execute within user process context, right? It executes separately. Like process switching function is one of them. That is dispatcher. So system processes, they execute in kernel mode only. Like, if you are aware of this process called init process in Linux or Unix, are you aware of this init process? That is process with ID 1 in Linux. Okay, fine. So if you see, that is what I am trying to say. Okay, let me know how many of you have already started working on Linux system. Okay, when you raise the hand, what should I understand? You are telling that you have started? That is what I should understand?
Yes, sir.
Okay, fine. So quite of you have started working with Linux system. And let me know, how was your experience? I mean, how it is? How is it going? Are you able to understand the Linux system? Are you able to understand? I mean, are you able to perform the laboratory programs? I mean, whatever the task is given in laboratory. Okay. I mean, 2 labs are already gone and you have performed few commands and simple shell scripts, right? If I'm not wrong. You have performed a simple shell script program, right? So in Linux, what happens when system is booting? The very first process which is created, that is process with ID 0, and that is called swapper process. That is called swapper process. Okay, and that swapper process creates new process, that is process with ID 1, that is called init process, and that is the parent of all other processes that you have in your system. Because in Linux and Unix, what happens? There is a system call called fork, and one process creates another process, and that is how all processes within your system gets created. Whenever you log in, that init process with ID 1, it creates new process for you, and then after you work within that structure. So that is the idea, that there are some system process like process 1. Okay, that is a system process, it is not user process, and that kind of system process works only in kernel mode. Okay, it does not get executed in the context of any user process, because it was there before any user process. So there are some processes like dispatcher and this kind of init processes which execute only in kernel mode. And what are the user processes? User mode to execute user programs and utilities. Okay, user processes execute in user mode, where you are executing your programs and utilities, like what we are doing right now. I'm executing this Zoom meeting, and whatever program you are executing, whatever application you have, they all are executed in user mode. Kernel mode to execute instructions that belong to the kernel. And while you are executing all this, for an example, when I'm running this Zoom meeting, internally it is using some network modules so that I can send data, I can receive data. So those network modules, which are very privileged modules, while they are being used by Zoom meeting, internally my program gets switched from user to kernel mode. That part gets executed, receive the data, let's say, and give it back to user mode, and then user mode again I am back, something like that. So that is mode switch happens when certain OS function need to be executed. So this is the idea, or this is the design, how OS SVR, or how Unix SVR4 is designed. This is the design of Unix SVR4 by process perspective. Then we have process state transition. Now, if you remember, we have already discussed state transition diagram before this also, but they were general. That was the general discussion. And now this is specific to Unix system. Lastly, we discussed 7-state diagram. In general, 7 states we discussed. Can anyone tell me what are those 7 states? Yes. Do you remember those 7 states, process states? I want answer from you people. New, ready, run, not run, it is running. Yeah, running, termination or exit, fine. There are 4, these are the 4 stages. Block, 5th one. Yes, ready are 2, ready, suspend and ready running. Sorry, ready, suspend and ready, fine. Block and block, suspend, correct. So almost all 7 are considered, right? Fine. So these are the 7 states that we discuss. Now almost those same 7 states are there, but there are 2 extra states. So let us discuss them. Okay, can you see this diagram properly on your screen? Okay, fine. So you can see that this is created or new state. This is created or new state as per our general design. Okay, and you can see fork I have written here, not I have written, but this is the diagram from the book itself. So they have mentioned here fork. So fork is a system call that you can use if you want to create new process by your own program. So when you call fork, new process will be created. So this is created state. And if you remember in 7th state also we mentioned that the newly created process can go either of the states. That is either directly to ready to run state, that is in memory. If there is enough memory, then it will be put directly into the ready to run state. If there is not enough memory, then newly created process may be put into ready to run suspended state. Ready to run suspended, or you can say ready suspended. So that is already there. And then you can see swap out, swap in is also there, that we discuss in 7 state diagram. So this is specific to Unix. Then you can see that we have two blocking stage. Here they call it asleep state or sleep state, right? Blocking or sleep, everything is same. So this is sleep state in memory. This is sleep state, suspended state. So when sleeping process, which is suspended, when it wakes up, it will go to ready state in suspended stage. When sleeping process, which is in the memory, when it gets wake up, when it wakes up, it goes into the ready to run in memory state. So these are the same things, and this is also possible. The sleeping process in memory may be swapped out and put into the secondary memory. So all these stages we have already discussed, all these transitions we have discussed in 7 state, right? Now there is one more zombie. This is exit state. When you exit any process, it enters into the zombie state. Zombie state is process is gone, process is executed, it is no more there, but some related data structures to that process is still there in the system, which can be used by operating system or the parent process for some reason, some accounting reason, some monitoring reason, whatever. For that states are, I mean, that data structures related to that exiting process is still there, and that is why it is called zombie process. Once this data structure is vanished out, okay, it is flushed out, then it is completely gone. So that is similar to exit state. So you can see this 3 and 3, 6, total 6 states from the 7 state diagram we have discussed. Now the only state that we haven't discussed according to that 7 state is running state. But now here you can see that the ready to run state and running state, okay, there are two ready to run state and there are two running state. Actually, it's a single processor system, so there can be only one process in the running state. But if you remember in Unix process, either it can run in user mode or kernel mode. So when see this two states, it represents the running process only. But if process is running in user mode, then it is in this state. But if it enters into the kernel mode, then it is represented here. And you can see there is arrow from here to here as well as from here to. So when it goes back from kernel mode to user mode, it will enter into this state. So now running state is divided in two parts, user running state and kernel running state. And these are the possible reasons for this system for this state transition. When running process enters from user running state to kernel running state, so some reasons like system call is there or some interrupt needs to be handled. So at that time it happens that. Then one more transition is there from kernel running to kernel running. Actually, your process which is executing in kernel mode to handle something, in between some new interrupt comes, and kernel has to handle that also before that because it is higher priority interrupt. So in that case, kernel will execute another process or another procedure, another function within the kernel mode, okay? And that is why kernel requires kernel stacks, because there can be multiple functions which can be executing within kernel mode from one to other, and that is why kernel stack is also required. So that is one more transition from kernel mode to kernel mode or kernel running mode to kernel. So basically these two are running mode only, and at a time a process can either be in user running mode or kernel running mode. It cannot be in both the states. The single process at a time, it can either be in user running state or kernel running state. So though here it is shown two different states, but actually it is only one state. At a time it can be only in one state. Similarly, these two, they both represent ready to run state. But there is some small difference between these two. Normally, what happens? Let's say your process, it enters into the kernel mode to execute something. Now, while it is coming back from kernel to user running, now while it is ready to come back from kernel mode to user mode after completing whatever it has to do, let's say because of some reason, that process needs to be switched. That process needs to go out. That is called preemption. Let's say your program is running and it has asked for the file. It wants to open a file. So it goes in the kernel mode to open that file. Once that file is open, now your process is coming back from kernel mode to user mode. But before it comes to the user mode, some higher priority process comes, some interrupt comes. Because of that, your process needs to be switched. Or let's say your process time is over, whatever. There is some interrupt because of which your process needs to be switched. Okay, and at that time it will be preempted and it is put here in preempted mode. But ultimately this preempted mode, it is also representing same state as ready to run. Okay, these two are actually managed in a single queue. Just for logical difference, what is the idea? When this process can be preempted, it can be preempted only when process is coming back from kernel to user mode. When process is ready to come back from kernel running to user running mode, at that time only it can be preempted. Otherwise it cannot be preempted. Otherwise it is also nothing but the ready to run process. Does this make sense? Does this diagram make sense to you? So these are the all states that we just discussed. Now let us talk about the process image. We have already discussed about process image in general. Now we will be discussing process image in UNIX. Okay, can anyone tell me what are the elements of process image that we discuss in general? In general process image. Do you remember the elements of those? Anyone? Process image. What is there in process image? I want answer from you. I am waiting. PCB is one of them, right? PCB is one element, correct? What else? Process ID and all those, that is part of PCB. User program, PCB, user stack, and one more thing, user program combined with user data. So that is called user space. That is called user space, program and data. PCB is there, user stack is there, and shared memory. And shared memory, isn't it? Okay, so that is in general, these are the contents or elements of any process image. But now see, very similar data is required in any operating system. The only thing is, yes, someone wants to ask something. Fine, very similar data is required almost by all the operating system. The only thing is they may be organized in a different way. Okay, so that is exactly what we are going to see in UNIX. Almost all this data are required, but they are organized in a different way. So what is that? A process in UNIX is a set of data structures that provide the OS with all of the information necessary to manage and dispatch processes. And that is actually applicable for all the operating system. The elements of the process image can be organized into three parts. Now, the image of the process image in UNIX system it can be organized in three parts. One is called user level context, then register context, and system level context. These are the three parts. So what is user level context? What kind of information is there in user level context? This is very similar to our user space, where you have program text or process text, then you have process data, that is the data which is used by the program, then user stack is there, and shared memory. So all these four, that is part of user level context in Unix process image. Okay. Then register level context or register context, which is very similar to processor state information in PCB. Similar to that, it is maintaining different registers like program counter, processor status register, that is PSW. In some cases it is called PSW, processor status word. Basically it contains different flags. Okay, and it depends on the hardware. So processor state register, status register, then stack pointer is there. General purpose registers are there. The general purpose registers are nothing but those user visible registers that we discuss in general design. Okay, so these are basically some registers which are managed within the process, Unix process. And stack pointer, again, as we are talking about Unix process image, and Unix process image contains two different types of stack: user stack and kernel stack. User stack and kernel stack. So at the time, whether process is running in user mode or kernel mode, accordingly this stack pointer is pointing to that stack. Basically it is pointing to the top of the kernel stack or user stack, depending on the mode of operation at the time of preemption. Then third is system level context. Now this is the most important part. This first two are very simple to understand, what kind of data it is managing or maintaining. System level context, so you can see most of the things that we have in PCB, they are here. Most of the things, not all. Okay, process table entry is one data structure that is there in system level context. What is process table entry? It defines state of a process. This information is always accessible to the operating system. You consider that most of the PCB information are maintained in process table entry plus U area. U area is another such structure. It is process control information that needs to be accessed only in the context of the process. Now, if you remember, PCB is divided in three parts: process identification part, processor state information, and process control. So that third part, process control information, most of the process control information are there in U area, and some static information regarding that process, it is there in process table entry. This process table entry is always there in the main memory, and U area information regarding process of U area of that process, that will be accessible only when your process is in a running state. Then only U area of that process is accessible. Otherwise, if your process is in any other state, only process table entry is accessible by operating system, and it will give sufficient information. But U area information will be accessible only when your process is in running state. There is one more, per process region table, which manages the memory. Whatever memory area is given to your process, those memory will be managed by this kind of data structure, per process region table. And then finally kernel stack is there, which is part of system. So that is maintained in system level context. This process table entry and per process region table, these are the static data structures. These are the static data structures. They are always there and they are not changing. Whereas U area and kernel stack, they are dynamic data structure, because U area contains certain information which gets changed, and kernel stack, definitely it's a stack. So whenever there is one procedure calls from other procedure within kernel mode, this stack will be changing. New entry will be pushed. When it is over, that entry will be popped. So it's a dynamic data structure. So first and third, they are static data structures. Second and fourth, they are dynamic data structure. So all in all, Unix process image contains three things: user level context, register context, system level context. And the most important thing, this system level context, again, we are not going to understand all this in very detail, but of course I am giving you some idea what is process table entry and U area. These are the two important things. Process table entry, it contains general fields of processes that must be always be accessible to the kernel. Whereas U area further characteristics of the process only need to be accessible for the running process itself. That is what I have already discussed. And these are some of the information that are maintained in process table entry, like process states, in which state the process is right now. What are the pointers? I mean, pointers to the U area and process memory area. Process size, what is the size of the process? User identifiers, actually which user created this process, and effective user ID. There is a concept called effective and real user ID in Linux as well as in Unix. Sometime we will discuss that also. Process identifiers are there, process ID, parent process ID, and all those. Event descriptor, if this process is blocked or sleeping, on which event it is sleeping, that kind of information is there. Priority of that process. Signals, there is a very good signal mechanism in Unix system. Okay, timers are there, some other links are there, memory status. So these are some information which are managed in process table entry. Whereas what is maintained in U area, there is one pointer from U area to PTE also, process table entry. From process table entry, there is a pointer to U area, and from U area, there is a pointer to PTE, and that is required for OS to manage the process. Again, some user identifiers are also managed here. Timers are also managed. Signal handler array. Signals were there, but the signal handler array is here. Control terminal, error field, return value, IO parameters, file parameters. So many other informations are there. Again, it is not possible to discuss all these things in detail here because it is itself a wide topic. I'm just trying to give you an overview of Unix process design. And these are the data structures which are internally linked. So you can see here, this is our process table. If you remember, for every process, there is a single table where all processes entries are there. And this is one entry for your process. So this is PTE. This is process table entry, which is there in process table. Okay. And this PTE is also connected to U area. You can see double pointer. U area is pointing to PTE, PTE is pointing to U area. So this is some dynamic information regarding your process. And there is one memory which is in the kernel, one memory area which is allocated for U area. So whichever program, whichever process is running, U area of that process will be loaded in that memory. So at a time, only one process U area is there. Then this is per process region table. Basically, it is related to memory management of your process. So your PT has pointers to that. Your PT will tell you in memory where your process is, program data is, kernel stack is there, where it is. So everything is managed. And this per process region table, this is per process region table, but that is part of kernel region table. So this is a bigger data structure. This is for all. This is for all processes, and this is for your process. So your process region table, it is managing, it is maintaining some pointers to the actual kernel region table. And then this kernel region table, basically, these are the virtual memory, okay? These are the virtual memory, and they are pointing to some actual memory area, actual main memory addresses. So of course, this is not that simple to understand, but you can just try to visualize that how complex it is. It is not that simple, how they are interconnected. So just to manage a process, you can see how many data structures are used and how they are complexly connected with each other. Are you getting some idea? I'm not asking for the everything. I'm just asking you, are you getting some overview, some idea how it is happening, how process is designed, how process idea is designed? Yes. Let us discuss very quickly process creation in Unix. So process creation is by means of the kernel system called fork. As I told you, by system called fork, new process can be created. This causes the OS in kernel mode to do something. There are few steps. Whenever process gets created, what happens? First of all, it allocates a slot in the process table for the new process. A new PTE will be created basically. Assign a unique process ID to that child process. Okay, assign a unique process ID to the newly created process, which is a child process. copy of process image of the parent with the exception of any shared memory. Okay, now this is interesting. Normally, when you use fork system call, a new process will be created. That new process, which program it is executing new process? Normally, let's say you have written one C program and you are executing that. So that process contains that program which it needs to execute. But if you create new process, which program that new process will execute? Any idea? Which program the new process will execute? Basically, what happens when you create new process, whatever the code is there in parent process, same code is copied in the child. Basically, the whole image will be copied. So copy of process image of the parent, the whole process image is copied in the child process. So whatever process parent process was doing, same thing will be done by child. But if you want, you can change that also. Increment the counters for any files owned by the parent to reflect that an additional process now also own those files. So whatever files and descriptors were owned by the parent process, they are also owned by now child process. So one more process is there which is owning those files. So counter is managed for those files, that okay, how many owners are there for this file. So that counter will be incremented. Assign the child process to the ready to run state. Okay, assign the child process to the ready to run state. Returns the ID number of the child to the parent process. Now newly created process, which is child process, it has some ID, and that ID will be returned to the parent process. And what is returned to the child process itself? Zero value to the child process. So when child process will execute, when it will complete this fork, it has return value 0. It means that is child process. And if non-zero value is written, then it is called parent process. So once now there are two processes, parent process, which just created child process. So what will happen after this creation? Which will run? Once parent creates child process, now which will execute next? Will parent continue, or child will be executing just after that and parent will be on the hold? It will be put in the ready to run. What happens? So it depends on it all depends on the situation. And there is any possibility like your execution stays in the parent process. So your parent process continues to execute after creating child process, or the execution transfer control to the child process and parent process will move to the ready to run state. That is also possible. And finally, it is also possible that neither parent nor child, after creating child process, parent and child both are moved to the ready to run state, and OS may decide to execute some new process, some other process. So all these three possibilities are there. So you can't control that because that is part of dispatching or the scheduling. So you can't control that, but fork is a system call which creates process, and these are the steps which are performed. See, I haven't mentioned about how those data structures, how this data structures will be initialized and what will be assigned into that. I haven't mentioned that, but everything is happening there behind the scene. So these are very broad, you can say very, basic steps that I have mentioned here. What happens when new process is created? And these are the references that I have used to create this PPT. Mainly first book, that is your textbook, Operating System Internals and Design Principles by William Stalling, and another book, The Design of the Unix Operating System by Maurice J. Bach. This is the standard book to understand Unix design. Just have a look on this book. Just have a look and you will understand how complex it is. Okay. So this is all about the introduction of process. What I would say here is introduction. No way we are discussing the details of process management. Okay. There is no way that we are discussing its details. This is just overview of process management design. And this is chapter number 3 that I just completed from your book. So within 3 lectures, I tried to complete this whole chapter. You just go back and read the whole chapter, and you better come with your questions. Otherwise, this will become very boring for you. If you do not understand, if you don't ask question, if you don't get your doubts clarified, it is of no use. You are basically wasting your time then. Okay. So Ask your question if you have and let me try to answer that. Any feedback that you would like to give here, anything that you want me to do, please speak about that. We still have few minutes, so if you have anything to say, please speak about that.